Okay, so now let's talk a little bit more about inflection points. Notice that I think I'd like for you to think about inflection points maybe as being akin to local mins or local maxes, in that not every zero for the second derivative is necessarily an inflection point. So the places where the second derivative is zero or the places where the second derivative does not exist, I'm going to call those partition points rather than inflection points. An inflection point is a place where the second derivative actually changes sign. Just like a local min or a local max are places where the first derivative actually changes sign. Okay, so let's look at the example down here. Example 5, it says, consider this graph. What is or are the inflection points? So again, the inflection points are where the concavity actually changes. So it looks like the concavity is up on this region roughly, and then the concavity is down on this region roughly. So I think it's a little hard to say, but it looks to me like the concavity probably changes around here. So I would guess that there's an inflection point at x equals 1. And just like with critical points or local maxes or mins, you're just going to report the x coordinate where this happens. So if we wanted to talk about where the concavity was up or the concavity was down or where there's an inflection point, we're just talking about the x coordinate where that happens for this function. So here the x coordinate seems to be about 1. Now, in problem 6, we're looking for the same sort of information. So we want to know when this function f is concave up, when it's concave down, and where the inflection points are. But in this case, they haven't given us a graph. So if you don't have access to a graph, what we have to do is just find this information algebraically. And we can do this in a similar way to what we did with the first derivative test. So there we just computed the first derivative and set it equal to 0. Or we figured out when the first derivative would be positive or negative. And we're going to do the same thing here, but this time we want to compute the second derivative. So to compute the second derivative, we're just going to compute the first derivative and then compute a derivative of that. So we first compute the first derivative. The derivative of f would be a 4x cubed by the power rule, and then a negative 6x squared, and then a negative 36. So I'm just taking the derivative of each term in f. And then I can compute f double prime. When I compute f double prime, I'm just taking the derivative of the line above. So if I take the derivative of 4x cubed, I would get 12x squared. If I take the derivative of negative 6x squared, I would get a negative 12x. And then the derivative of negative 36 would be 0. So I'm just going to leave that term off. And now we're interested in when this f double prime is positive, when it's negative, and when it's equal to 0. So generally, whenever you want to know whether something is positive or negative or equal to 0, it's a good idea to try factoring it. So I noticed that 12x is a common factor between these two terms. So I'll go ahead and rewrite f double prime as a 12x times an x minus 1 if I just factor that 12x out. So from here, it's a little bit easy to see that the roots of f double prime are going to be at 0 and 1. Those are the two places that I could plug in an x value and cause a 0 for f double prime. And if you'd like, we could just graph f double prime. So if you remember how to graph quadratics that look like this, notice that this is a quadratic that opens upward because its leading coefficient is positive, and we also know that it goes through the points 0 and 1. So f double prime is going to look like this. In particular, f double prime will be positive over here, and then negative between 0 and 1, and then positive again over here on the right. But you can also determine that information in the same way that we did whenever we were using the first derivative test. We can make a little number line for f double prime, and then we can plug in a test point in each of these regions if we wanted to. And if you were to do that, to plug those into f double prime, what you would get is f double prime is positive and then negative and then positive. So if you don't know how to graph f double prime immediately, it's okay to just make a little number line like we did for the first derivative test. Okay, but now that we have this information, we're trying to go back to the original function f, and we want to know when it's concave upward, when it's concave downward, and the coordinates of the inflection points. So first let's decide the intervals on which f is concave upward. So that happens when the second derivative is positive. And as we've seen either from this number line or from the graph, we know that f double prime is positive if you are smaller than 0 or positive if you are bigger than 1. So I would write that in interval notation like this. F will be concave upward between -infinity and 0, and then it will be concave up again once we pass 1. So that will be from 1 to infinity. So that's where we're concave upward. Now the original function f will be concave down, or concave downward, only whenever the second derivative is negative, and that only happens between 0 and 1. So we're going to be concave down between 0 and 1. And then we want any inflection points. Now notice that an inflection point is where the concavity changes, and that means that the sign of f double prime changes. So we're looking for the places where f double prime changes signs. And you can see that either from this little number line that I've drawn or from the graph of f double prime if you're comfortable just graphing the quadratic. Either way, you see that the sign of f double prime changes at 0 and it also changes at 1. So the inflection points are going to be x equals 0 and also x equals 1. So that answers the question of this concavity. So where is the original function f concave up or concave down? And it also answers where the inflection points are. There are 2 inflection points in this case. So in the next video, we'll talk about how to apply the second derivative test. The idea behind the second derivative test is just that we're still going to be looking for these local maxes and local mins, but this time we can use our concavity to our advantage. Rather than looking at the signs of f prime, what we can do is we can just decide if we're in a region where the concavity is negative or concavity is positive, and that will determine whether we're sitting at a local max, which would be this picture with concave downward, or a local min, which has upward concavity. So we'll start that in the next video.